Swayam Prabha. Digital India. Educated India.
Students, we have had 3 lectures so far on this topic of shear strength of soils. Today we will go on to the 4th lecture. Let us take a look at the first slide, which describes what we have seen in the past. We have seen basically that this topic of shear strength of soils needs to be studied in essentially 3 stages. Number 1 is understanding the behavior under shear depending upon the type of test or depending upon the type of equipment that is used for testing shear strength. Secondly, the drainage conditions used in the test depend very much and influence very much the behavior of the soils under shear. And lastly, we need to study the shear strength according to the type of soil, because behavior of cohesionless soils is quite different from behavior of cohesive soils under shear. Having classified this topic of shear strength into these 3 basic categories, we had started looking at the first category, that is the type of equipment or the type of test that is used for determining shear strength of soils. Under that, if we go to the second slide, we will be able to recapitulate that we have already gone into complete detail of the shear strength test known as the direct shear test, DST. We had also seen an overview of triaxial shear test, TST. Of course, in one of my early lectures, the first one perhaps, I had also given you a general idea about the next 2 tests, the unconfined compression test and the vane shear test. Today, what we shall be doing will be to quickly recapitulate briefly what we saw under direct shear test, then again recapitulate what we had studied under triaxial shear test, and then go on further to get into the nitty-gritty and details of the triaxial test and also do some examples. So, if you remember, this was the basic schematic diagram of a typical direct shear apparatus. You can see there that there are 2 parts in this, the lower part and an upper part separated at the junction here like this, and the soil specimen is also a split specimen, and this specimen is sheared by applying a tangential load, a shearing force here. Of course, a normal load is also applied to keep the specimen confined. Then there are of course other small additions, such as the dial gauge here to measure the volume change, the dial proving ring here to know the force that is applied, porous stones here to permit drainage, and a displacement gauge to know the displacement that the sample undergoes. All these together constitute the entire shear strength apparatus known as the direct shear apparatus. Then we also saw that the results of a direct shear test can be analyzed and can be interpreted with the help of a Morse circle. The principle of the Morse circle was explained to you in very great detail by me in one of the earlier lectures. So, today we will just quickly see a typical Morse circle, particularly the way it looks for a direct shear test. You know that a Morse circle is this, the point A corresponds to the minor principal stress, point B corresponds to the major principal stress, and the point OP, which is obtained by drawing a line parallel to the plane of sigma 1, gives the pole OP, because by definition pole is a point on the Morse circle which has coordinates sigma and tau, which in turn are equal to those on a plane passing through that OP and the point A. So, it so happens that this red line which passes through A and OP is nothing but the minor principal plane, and therefore, point OP represents the stresses which act on the minor principal plane. And now, from this OP, if you draw a line horizontal OPC, then since it is horizontal, it will be nothing but the representation of the failure plane. In a direct shear test, as you remember, this failure plane is an imposed plane, a horizontal plane, and C will then be having coordinates which are equal to the normal and shear stresses on the failure plane. Okay. Now, from this one can find out the values of cohesion and friction. Being a direct shear test which is drained where drainage cannot be prevented, we only get an angle of friction phi, cohesion is 0. Okay. Now, let us take a quick look at triaxial test the way we have seen it in the earlier lecture. This is what a typical triaxial apparatus looks like. There is a loading frame, there is a cell which contains the triaxial specimen where the so called triaxial stress state is achieved. Below that, there is a motorized unit which drives the platen upwards, the base upwards, thereby imposing a vertical load. And then of course, there is a proving ring to measure the vertical load and a dial gauge and so on. Let us see a little more detailed diagram, a schematic diagram rather than this photograph. This is the schematic diagram of a triaxial apparatus. You see here, starting from bottom, taking the right hand side, this is where we have the pedestal, and from the pedestal there is an outlet here, rather an inlet which is attached to the pedestal, you can see here, through which we apply the cell pressure. That cell pressure gets applied on the specimen inside this cell. So, this perspex cylinder here, that is the so called cell. On top of the specimen here, we have a loading platen, and so also at the bottom. At the bottom, in the pedestal, there is also an outlet which goes to the pore pressure measuring unit, and there is a pipe here which goes into the soil specimen. So, the pore pressure inside the soil specimen gets reflected here in the pore pressure measuring unit. Then there is a rubber membrane which holds the specimen in place. Then of course, we have an air vent to ensure that the water that is stored here through which the lateral pressure is applied is free of air, and then we have the proving ring to know the vertical load applied. This shows the stresses that act on the typical triaxial test specimen. The way the test is conducted, as we have seen earlier, is first of all a radial all round pressure is applied, that is known as the cell pressure sigma r. It is acting on the circumference of the specimen, and after this the vertical load is increased until the specimen fails, and therefore, at the end of the test, at the point of failure, we will have an all round pressure sigma r, which incidentally being water, it also acts at the top and the bottom, and then this stress sigma r is increased by an amount known as the deviatoric amount, so as so as to get the total axial stress sigma 1 at the top and bottom at the time of failure. So, having seen this quickly, let us move on to today's lecture. In today's lecture, I plan to go further and talk a little more about details of the triaxial shear test and see a few problems, and then move on to the unconfined compression test, and then finally the vane shear test, and everywhere we will understand the principles and the method of utilization of the test through some examples. Basically, all these tests ultimately are intended to give the shear strength parameters C and phi. If they are total stress parameters, they are C and phi, and if they are effective stress parameters, we generally refer to them as C dash and phi dash. So, we will see a few examples which involve determination of the effective strength parameters or the determination of the total stress parameters. So, more about the triaxial tests. Okay. Let us see the components of a triaxial apparatus by flitting through a few photographs again. What we see here are the major components of a triaxial apparatus. I have highlighted here the lateral pressure and the vertical load units. Here is where we have the lateral pressure unit, and here is where we have the vertical loading unit. So, using the same terminology which we used in one of the earlier photographs, we have here the cell, we have here the platen, we have here the loading frame, and then below the motorized vertical load application unit, and on the left you have a compressor which develops the air pressure that is required to apply the lateral pressure. So, this is the lateral pressure unit, and then lastly we have the pore pressure measuring unit to know the pore pressure at any stage of loading or any stage in the test that is developed inside the specimen. Another photograph, a greater detail of the motorized vertical load unit. We have here the facility to control the speed of this motor, so that the movement of the platen upwards is controlled in a strain controlled manner. So, by adjusting the strain in the upward direction, we can control the load that is applied in the vertical direction. Here is the loading frame, the cell and the motorized unit and the pore pressure unit all together, one of these views. Here we have slightly closer views of the compressor and the lateral pressure unit. Compressor develops the air pressure that is required to drive the water under pressure into the cell. From here the air pressure comes through this, and the pressure is applied to the water which goes out through this into the triaxial cell. This is the pore pressure measuring unit. Now, in the case of a triaxial test, we need perfectly cylindrical specimens whose ends are quite planar, whose sides are perfectly vertical, because it has been found through experience that a specimen which does not enjoy these benefits or these characteristics sometimes gives errors in the final results. Sample or specimen preparation is therefore a very important aspect, and here is an unit which is meant for extracting a sample from a core box that is brought from the field. We extract a core from the field, and then from that we take out a sample. From the sample we then cut out a specimen. Here is where what we have the specimen, and the specimen is taken out of the split mold. That is, if you go back to the earlier slide, when you extract with the help of a plunger the core out of this core cylinder, then what you get is collected, what comes out is collected in a split mold, and then because it is a split mold you can open it out and take the sample out. And once the sample comes out, you can cut it to appropriate sizes, and together with these platens it can be put on the loading machine. Here we have a closer view of this split mold and the specimen holder in the triaxial apparatus. Now, What are the kinds of stresses and strains that develop in the triaxial test when we apply the so called radial pressure and the axial pressures? So, first the cell pressure is applied in the form of a radial pressure, and then the pressure is increased in the axial direction until failure takes place. So, the radial pressure is say sigma r and the axial stress is say sigma a. Obviously, since no other pressures are acting, the radial pressure is going to be the minor principal stress, and the axial stress that is applied is going to be the major principal stress, respectively acting on a vertical plane and a horizontal plane. The difference between these two, sigma d, is known as the deviatoric stress, and it is therefore equal to the sigma axial minus sigma radial. And since the axial stress is nothing but the major principal stress and the radial minor, we have sigma deviatoric is sigma 1 minus sigma 3. Further, the stress sigma r that is applied all around is nothing but a confining pressure that confines the sample, and the reason why we apply this is this helps us to simulate the confining pressure that exists at the depth from which the sample has been taken out. Since the behavior of a soil under stress is very much controlled by the stress that it has experienced in situ, we must recreate the in situ stresses in the specimen that we used in the lab, and that is the reason why we apply a confining cell pressure sigma r, whose magnitude is equal to the confining pressure that is expected to be existing at that depth from which this specimen has been collected. Now, this stress condition inside the specimen, which is basically sigma r and sigma a, depends on the drainage conditions. If drainage is permitted from the specimen, then what happens is, as the water expels out, there is a compression taking place. A volumetric compression takes place in the specimen, and as the water goes out, therefore effective stresses develop in the specimen. So, as the test progresses, if it is a drained test, then the effective stresses in the specimen go on increasing. So, if we are applying stresses sigma 1 and sigma 3 to start with, at the end of the test we will have the effective stresses sigma 1 dash and sigma 3 dash acting on the specimen. If on the other hand we have the undrained conditions, then since drainage is not permitted, soil volume does not change, it remains constant, and therefore pore pressures get built up in the water inside the specimen, and effective stresses are not allowed to develop. So, in an undrained test, purely undrained test, the initially applied stresses sigma 1 and sigma 3 remain as total stresses, and the total stresses remain the same at the end, and effective pressures are not mobilized. So, this shows the stress conditions through a Moore diagram which exist in a triaxial test. In a typical triaxial test, as we have seen, we will be having the minor principal stress and the major principal stress. Generally, we conduct at least 3 tests on any particular soil. So, here we have the minor principal stress and the major principal stress and corresponding circle for one pair of these stresses. Then we can apply another cell pressure sigma 3 2, get a corresponding failure axial stress sigma 1 2, so also a third one. So, the test is conducted on the same soil under 3 different confining pressures, and 3 different Moore circles are obtained corresponding to the 3 different failure axial stresses. Now, if I take a common tangent to all these and assume that the Moore-Coulomb failure criterion is valid for this, then what we will have will be an intercept which represents the cohesion in the soil, and an angle here, the angle of internal friction phi, and the stress state in the triaxial test, if that is known, then we can plot these graphs and we can calculate the shear strength parameters. That is the reason why we need to understand correctly the state of stress in the specimen at any given time. Now, what happens to the strains? By measuring the change in height during the axial loading and the change in volume during the lateral loading, we can determine the strains. If we assume that this cylinder, the cylindrical specimen remains like a cylindrical specimen even after deformation, then we can derive simple expressions for the volumetric and axial strain. It is very obvious that the volumetric strain will be epsilon V equal to minus dV by V0, where dV is the change in volume. Now, the change in volume can be easily measured from by attaching the pore pressure unit, and the original volume V0 is supposed to be known for the specimen, and therefore, epsilon V, the volumetric strain, can be easily computed. Then on the other hand, the axial strain will be the change in the vertical height of the specimen divided by its original height, epsilon A. And since on the vertical compression the area of cross section of the specimen increases as the specimen gets compressed and its diameter increases, the new area of cross section, which will tell us what is the new stress state, will be given by this expression. In terms of the vertical and volumetric strains, you can, and the original area of cross section, we can get the new area of cross section. So, A is the new area of cross section after deformation, A0 is the initial area of cross section of the specimen, and H0 is the initial height of the specimen. With this, we will be able to tell what will be the strains at any given instant in the specimen. So, the sum total of all this is, during the experiment there will be some stresses and strains developing. The stress state can be expressed in terms of the Morse circle as shown here, whereas the strain state can be expressed in terms of the variation of the deviatoric stress with the function of the, as a function of the axial strain epsilon A. This shows that the deviatoric stress goes on increasing and the axial strain also goes on increasing up to a point, beyond which the deviatoric stress comes down because the soil would have already reached its failure strain value and the stress does not get built up anymore. Okay. Now, why do we need to conduct this triaxial test? Why do we need to understand the importance of this triaxial test? It is because there are several advantages associated with the triaxial test compared to the direct shear test. The advantages are: 1, real situations of confinement in the field can be simulated. As I mentioned just a few slides ago, a soil is under a certain confining stress at a given depth in the nature, in the field. Now, when you extract a sample from a certain depth and cut a specimen out of it and test it, obviously, in order to simulate the conditions which it experienced in the field, we need to know what was the condition of confinement and reproduce that in the experiment. And the triaxial test helps us to do precisely this, because we can apply a cell pressure of any known magnitude which will simulate the confinement that this sample is experiencing in the field at a given depth. Then the manner in which the pressures are applied here gives us the facility to have fairly uniform stresses inside the specimen. The direct shear, if you compare, for example, as the specimen deforms, you will find that the area over which the normal stress is acting goes on changing. Therefore, the stress level goes on changing, it does not remain uniform. Whereas, on the other hand, in the triaxial test, we have the advantage of imposing fairly uniform stresses on the sample. Then, most important, the shear strain behavior of the soil can be studied in detail. As the test progresses, you can measure the strain levels, volumetric strain and the axial strain, and compute the shear strains. Lastly, both drained and undrained conditions can be easily simulated in a triaxial test. In the direct shear test, on the other hand, we found that undrained conditions can hardly be simulated adequately, right. Then finally, pore pressures can be measured and effective stresses can be determined during the undrained test. This is a tremendous advantage, because the knowledge of the pore pressure tells us exactly what is the kind of effective stresses that are mobilized during the test, and the shear strength is a direct function of the effective stress, and therefore, knowledge of an effective stress is very necessary, and the triaxial equipment can really help you to get that. Let us quickly take a look at some examples. To begin with, let me take the same example which we saw in the earlier class. We had called this as example 6. So, let us see example 6, which we had already seen in the last lecture. It helps us to maintain continuity. So, that example which we saw in the last was data about a triaxial test on a saturated sample of sand. The cell pressure used was 300 kilonewtons per meter square, and in the test it failed at a deviatoric stress of 200 kilonewtons per meter square, and the pore water pressure was measured, and at failure it was found to be 175 kilonewtons per meter square. So, with the help of this, the shear strength parameters were determined. To determine the shear strength parameters, we can use either these total stresses or subtract the pore pressure which has been measured and get the effective stresses. And we can do this by plotting the Morse circle or by using the formula for the shear strength. Here, the example which is given makes use of the formula, but a Moore diagram can be easily plotted, and the student is advised to try that out himself and compare the results with the formula and find out how right he is. So, this is what the typical Moore circle looks like, and in a triaxial test. So, here we have the point corresponding to the major principal stress and the minor principal stress, and this is the failure plane at an angle of theta critical. Now, in terms of total stresses, we can say that tan square 45 plus 5 by 2 is equal to 500 by 300. Why 500 by 300? 500 by 300 is nothing but, you can see here, it is cell pressure plus the deviatoric stress, that is sigma 1, and see here 500. So, sigma 1 upon sigma 3, that is what we are having here. Sigma 1 by sigma 3 is equal to tan square 45 plus 5 by 2. This is an expression which we had seen in one of the earlier lectures, and from this we can get phi equal to 14.5 degrees. And if we wish to use the effective stresses, what we need to do is to subtract the pore pressure from the values of sigma 1 and sigma 3, and if you see go backwards, the pore pressure is 175, and coming back, if you subtract 175 from here, you have 325 and 125, which gives you the effective angle of friction phi dash equal to 26.4 degrees. We also saw another example, example number 7, which was very similar. Now, in both these examples, we considered a single test with one single sigma 3 and sigma 1. But as I mentioned a few minutes back, in a typical triaxial test, we always make use of several confining pressures and find out the corresponding failure axial stresses and plot more circles one after the other for each confining stress and find out a common tangent which will give us the failure envelope. So, let us see examples of that. Let us go to example number 8. In this example, we are having data of an undrained triaxial test on clay. So, undrained triaxial test means drainage is not permitted. Obviously, it means that the stresses which we have are all total stresses. And incidentally, in this example, pore pressures were not measured, and therefore, the stresses which we have or the stresses which we have are the total stresses, and in order to get the effective stresses, if we required, we need to have the pore pressure measurements. Now, the values of sigma 1 and sigma 3 are given here. Sigma 3 is this, the deviatoric stress is this. Normally, we apply confining pressures of these ranges, of these magnitudes. So, if I take these data and go further, I find that since pore pressures are not measured, we can only determine the total stress parameters. To determine the total stress parameters today, we will see two methods. One is of course the Mohr circle plot, about which we had talked earlier for a long time. Another is a so called PQ plot, and both of them can be used for determining the total stress parameters. Here we have the typical Mohr's diagram, that is, we have 3 stress values, minor principal stresses corresponding to 50, 150 and 250, and 3 axial stresses. What we need to do is to plot 3 different Mohr circles and then plot a common tangent. Now, that is not shown here, the Mohr circle plots are not shown here. However, the student may attempt drawing these Mohr circles and draw a common tangent. Alternately, we can use the so called PQ plot. What is this PQ plot? We know already this equation, the relationship between sigma 1 dash, sigma 3 dash, C dash and tan square 45 plus 5 by 2, that is n phi, or its equivalent, which is this. Now, you find this equivalent expression, that is the second expression, is a linear expression, and if you therefore plot half of sigma 1 plus sigma 3 along the x axis and half of sigma 1 minus sigma 3 along the y axis, we will get a linear relationship, which is shown in the next slide. Here we have half of sigma 1 plus sigma 3 and we have half of sigma 1 minus sigma 3 along the y axis. This is known as P, this is known as Q. Because it is a linear relationship, the PQ plot, as it is called, will be a straight line. Here I have an example of a PQ plot. What is special about this PQ plot is, if you go back to the basic equation, the slope of this will be given by tan phi dash and the intercept will be given by C double dash. So, this intercept C double dash is here and the slope of this line is given by the angle of inclination, which is phi double dash. Now, you can compare this equation with the basic equation which is given here, the original one, and you can show that C double dash is related to C dash and phi double dash is related to phi. That relationship is phi double dash is tan inverse of sin phi and C double dash is C cos phi. So, what this means is, ultimately we are interested in the shear strength parameters C and phi. By taking this straight line plot, we can find out sin phi, which is equal to tan phi double dash, and then from sin phi we can find phi. Then we have C double dash, which is equal to C cos phi. Knowing C double dash, which is the intercept here, we can always find out C, because phi is already determined from this. So, this is what is normally done in order to determine the shear strength parameters. So, now if I take the total stresses that have been obtained in this experiment, we have sigma 3 total stress, we have sigma 1 the total stress, and corresponding values of P and Q will be sigma 1 plus sigma 3 by 2, sigma 1 minus sigma 3 by 2, and these are these values. These values can be used for drawing the PQ plot. Here is the PQ plot. So, as we saw, the data of the problem is adequate enough to compute P and Q values and plot them. So, if you plot P and Q, this is the kind of plot you will get for the total stresses, and this being a straight line, you can fit a straight line through all the 3 points, and you can find out the intercept and the angle of inclination, from which you can calculate the cohesion and friction parameters corresponding to the total stress condition, that is the undrained condition, which are known as usually Cu and phi u undrained. So, in this particular problem we get 27.3 kilopascals and 15.82 degrees. This is the situation for total stresses, but since in this problem no pore pressures were known, we can only get total stresses and total stress parameters. Now, let us go further. If you plot the Mohr circle diagram, which is not shown here in the slide, you will find that you will get slightly different values of Cu and phi u compared to what we got for the PQ plot. In the PQ plot we got 27.3 and 15.82, whereas if you plot the Mohr circle diagram and get the values of Cu and phi u, you will find 29.0 and phi u equal to 15 degrees. A slight difference is always permissible because they are both graphical procedures, but by and large the PQ plot is preferred these days because a straight line can be plotted more reliably than a Mohr circle and a common tangent. And going by that statement, we can say that the values of Cu and phi u which we have observed from the PQ plot may be taken as the appropriate values for this particular soil. One more example. Here again a traxial test, an undisturbed clay sample, and confining pressures used were same 50, 150 and 250 kilonewton per meter square as in the previous example, but the deviatric stresses are different, 41, 112, 176, and the pore pressures were measured. The pore pressures at failure are 45, 105 and 160. So, this is a situation in which we are in a position to calculate the effective values of sigma 3 and sigma 1, and therefore, we can not only get total stress values P and Q, but we can also get P dash and Q dash, and therefore, we can get Cu phi u corresponding to the total stress condition and C dash phi dash corresponding to the effective stress conditions. Again, we can use either the Mohr circle plot or we can use the PQ plot. So, let us proceed. If I consider total stresses first, I find that I know sigma 3 and sigma 1 minus sigma 3, it will give rise to 3 values of sigma 1 like this. Since we know the pore pressure, we can subtract the pore pressure from the given values of sigma 3 and the computed values of sigma 1, and we will get sigma 3 dash and sigma 1 dash, and also sigma 1 dash minus sigma 3 dash the deviatric stress. Since the pore pressure u gets deducted from sigma 1 as well as sigma 3, the difference between sigma 1 and sigma 3 and sigma 1 dash and sigma 3 dash will both be same. So, the deviatric stress either in total stress or in effective stress manner, they are identical. Once again, either we can get the shear strength parameters using Mohr envelope like this, plot 3 Mohr circles, draw a common tangent, or you can get it from the PQ plot. If we use the Mohr circle plots, we can draw Mohr circle plots for total stresses entirely or for effective stresses entirely. If I were to plot the 3 Mohr circles using the total stress values and get the intercept and inclination of the common tangent, I will get 5 kilonewton per meter square as the undrained cohesion and 14 degrees as the angle of friction. If on the other hand I use sigma 1 dash and sigma 3 dash for each of these 3 tests, plot 3 more circles, draw a common tangent, I will get the corresponding effective stress, shear strength parameters, intercept and angle of internal friction as C dash equal to 15 kilonewton per meter square and phi dash equal to 24 degrees. You can find that there is a large difference here. That is what happens when you do not have drainage and when you have drainage. When you do not have drainage and measure the pore pressure, this is what you get. Now, suppose you want to determine the same thing using PQ plots, then the data for plotting the PQ straight line in terms of total stresses it will be this, because we already know values of sigma 3 and sigma 1. P is nothing but sum of the 2 by 2, Q is nothing but the difference between the 2 divided by 2. So, if we plot this value of P and this value of Q, we get the total stress PQ plot. So, here is the total stress PQ plot for this test, and from this the intercept and the angle of inclination will give us the undrained cohesion and the undrained angle of friction as 3 and 14 approximately. If we were to use the effective stress parameters, then the data that we need for plotting the PQ graph is sigma 3 dash is this after subtracting the pore pressure, sigma 1 dash is this after subtracting the pore pressure, P dash will be the addition of the 2 divided by 2, Q dash is the difference divided by 2. So, we now have P dash which is quite different from the value of P we had earlier, but Q dash however remains the same because it is the difference between the stresses, and as I pointed out a little earlier, sigma 1 minus sigma 3 is equal to sigma 1 dash minus sigma 3 dash. So, we have P dash and Q dash. If we plot them, we get the PQ plot for effective stresses, and from here, from this intercept and the angle of inclination, we can get the effective cohesion and effective angle of friction as 11 and 26 as shown in this graph. Okay. So, to summarize, we get undrained cohesion and undrained friction under total stress conditions from the PQ graph like this. The corresponding Mohr circle plots gave us 5 and 14. The difference is marginal, and this much difference does occur because of the two different ways of plotting. And as I said, PQ plot is always preferred because plotting a straight line is always easier and more accurate than plotting a circle and a common tangent. Similarly, under effective stress conditions, C dash and phi dash are like this for PQ plot, whereas the corresponding Mohr circle values which we got a little earlier are 15 and 24 degrees. So, this is what a typical triaxial test is all about. We conduct the test measuring the pore pressure usually. So, at the end of the test we will not only have the total stresses that we have applied, but also the pore pressures and therefore the effective stresses. So, we can calculate both the total stress strength parameters and the effective strength parameters. The utility of these strength parameters we shall be seeing in the next lecture, when we are going to look at shear strength in a different way, that is from point of view of the effect of drainage, undrained and drained conditions and their effects on shear strength. Okay. Let us move further, take another example. Example 10 is a test on rock, because the triaxial test can also be conducted on rocks. But what is important to note is the kind of stresses that are required to make a rock sample fail under shear in triaxial conditions are much higher than what we require for soils. So, in a drained triaxial test on a volcanic break shear, we get values of sigma 3 and deviatric stresses sigma 1 minus sigma 3, which are much higher than what are usually obtained in the case of soils. So, if sigma 3 dash is 5, 10 and 20 megapascals, deviatric stresses are 31.8, 42.2 and 68 megapascals, then sigma 1 dash will be 36.8, 52.2 and 80 megapascals. Now, from this data we can calculate P dash and Q dash and get the PQ plot. Since this is a rock sample, we seldom measure pore pressures in a rock sample because it is virtually impossible, and we get a PQ plot therefore in terms of the effective stresses. The PQ plot in terms of effective stresses for this rock gives us a C dash of 5 megapascals and phi dash of 33.34 degrees. So, this is the utility of the PQ plot. There is a lot of advantage in drawing a straight line through the test points than in plotting more circles and drawing a common tangent. Now, let us see one more example of triaxial testing. A clay specimen here is tested under a condition of full drainage. The cell pressure used is 80. Here the shear strength parameters are given, C dash and phi dash, the effective stress parameters. What is required is the compressive strength of the specimen. Now, that is, from shear strength we want to determine the compressive strength of the soil. It is possible from the triaxial shear test data. From lecture number 3, we know that there is a certain relationship that holds good in a Morse circle at failure. Let us see what that relationship is in the next slide. This is the Morse circle, and from geometry we can easily derive this relationship here, which holds good for a Morse circle at failure. C cot phi, that is what you will get here on the x axis when you produce this envelope and make it cut the x axis here. This is C, the angle which will be made here will be phi, and therefore the distance here will be C cot phi. C cot phi plus sigma 3 is the distance from the shifted origin up to the point A, and C cot phi plus sigma 3 plus sigma d, the deviatoric stress, that is, or df at failure, is the total length here. So, one divided by the other can be shown to be equal to 1 minus sin phi by 1 plus sin phi. This is simply a modified form of writing an equation which we saw a little earlier in terms of tan square 45 plus phi by 2. So, from this equation it is very easy to calculate C and phi, and that is what we will do. Compressive strength of a soil is nothing but the deviatoric stress at failure, df. So, straight away from this equation the unknown df can be calculated because sigma 3 is known, phi is known and C is known. So, if you substitute the known values, you will find that C cot phi is nothing but 27.47. This is sigma 3, C cot phi plus sigma 3 plus df. So, this is equal to 1 minus sin 20 by 1 plus sin 20, where 20 is the angle of internal friction which is known. This gives us df equal to 111.86 kilonewton per meter square. That is the compressive strength of the soil sample. Okay. Now, there are two other tests, the unconfined compression strength test and the vane shear test, which we shall see now. These two tests are primarily meant for clay soils. They can be done in the laboratory as well as in the field. So, if I take the unconfined compressive strength test, this is what the equipment looks like. It is a simple loading frame with the facility to keep a soil specimen and load it and test it to failure without applying any confining pressure. So, this is known as the UCS test. See here, an unconfined compression test is a special case of a triaxial test, because the only difference between the two is in unconfined compressive strength test sigma 3 is 0. Now, this is usually employed to test cohesive soils. Hence, an axial load is applied rapidly to failure. There is no confining pressure applied at all. Therefore, undrained conditions will prevail obviously, because the loading is rapid, which means the angle of internal friction will not get mobilized at all. That means phi u is 0. Therefore, the corresponding Morse circle for this will be a single circle which will pass through the origin. This semicircle is the Mohr circle, sigma 3 being 0, this point will coincide with the origin, and sigma 1 is the stress, axial stress at failure. If you draw a tangent to this, obviously this tangent here will give you the undrained cohesion, and sigma 1 minus sigma 3 is nothing but the compressive strength, and therefore, what you get here at sigma 1 is nothing but the unconfined compressive strength of the specimen, that is Qu, and it is from this that the name UCS test is derived. So, once you have this kind of a Mohr circle, you just measure the axial stress sigma 1, that is the unconfined compressive strength. Then what happens to the cohesion? The cohesion is nothing but the radius, that is equal to half the diameter, that is it is equal to Qu by 2. So, unconfined compressive strength Qu divided by 2 gives you the undrained cohesion. So, this is a very simple and very effective convenient method of determining the shear strength parameter and the compressive strength of a clay soil. It can be done both in the lab and in the field. Let us take an example. The example would involve a number of parameters which are described here, and the relationships are also given here. A0 is the initial cross section. There is a vertical axial strain that the sample undergoes. So, if you take that into account and calculate the modified area of cross section of the specimen, you will get AF. So, from this you can always find out what will be the final stress that acts on the specimen, which is what is required in order to plot the Mohr circle. Okay. Now, UCS requires a simple equipment. It is conducted in the field, and it is a method for rapid assessment of consistency of soil for its classification. Clay soils are classified according to their consistency based on the value of unconfined compressive strength as shown in this slide. Depending upon the value of undrained cohesion or the compressive strength Qu, the consistency of a sample is defined like this. Now, further, the strength, unconfined compressive strength of a soil depends upon the nature of disturbance that the soil has undergone. In the undisturbed state, if it has a compressive strength Qu undisturbed, and after remolding, if it has got an compressive strength of Qu, the ratio of these is known as sensitivity. That shows how sensitive the soil is to disturbance, because there is a reduction in strength due to disturbance. This value usually lies between 1 and 8 for clays, and for flocculated marine clays it can even go from 10 to 80. Let us take one quick look at an example. The clay specimen which was tested in UCS has these dimensions 38 mm and 76 mm. The vertical deformation was measured to be 10 mm at failure, and the load at failure was 0.25 kilonewtons. In order to compute Cu of this clay, all that we need to know is what is the final area of cross section corresponding to the strain, vertical strain, and then the load divided by the final area of cross section gives you the unconfined compressive strength of 192.31 kilonewton per meter square and the corresponding cohesion of 96.15. Now, we will probably take a look at the vane shear test in a subsequent lecture. So, let us now summarize what we have seen today. In this lecture today, according to the classification of shear strength based on the type of equipment used, we have completed seeing direct shear test, triaxial shear test and unconfined compression test and a few examples. In the next lecture, we will continue with this type of equipment used and see the vane shear test and proceed further with the undrained and drained conditions of testing. Thank you.